All right, so what I will, first of all, good morning to all of you. What I would like to do today is to continue with the material that we covered on Wednesday. And also, I would like to point out that I have placed um, the lectures from Wednesday on your homepage for the class. And also, I have uploaded all of the problems that we solved, and I believe the solutions for the problem solving session. And the one thing that I wanted to show you, for those who were not able to make it during the problem solving session, I wanted to show you. I will share my screen for a moment so you can see what I'm trying to do here. Not, it's not that really. I wanted to show this one and this one. So on the home page, if you go down, as I said, I'm trying to include everything here. So this is everything you need to have for this class. This one, and where I'm organizing the fact. So these two are the places you need to be looking at. All right, so here on Wednesday, we had the problem solving session. There are 3 topics that I have included here. And so you will see them here. There is problem solving session 3, problem 1. So look at this solution. It was like from what we have covered in the class. Problem solving session 3, also problem 2. Well, this came up, all right? So this is also, we solved this problem. And practically what we wanted to do is to find the potential difference and so forth in this coaxial cable, as we call it. This is like something that you find in many places. I don't know how many of you know what is a coaxial cable. Has anybody heard?
Yeah.
Okay. What is a coaxial cable?
Is that not the cable you use for like TV and stuff?
Yes, that's excellent, Eduardo. It's exactly this black cable that you see. It's thick, obviously. It's much thicker that you see we are using for the power for our to power our laptops and stuff. It's a thick black cable, and then outside, if you see the connection, if you look at the connection, usually I have to say nobody will really pay attention to how the connection looks like. But if you look at the connection, you will see that it has exactly this kind of. It looks like that. It has a pin at the center that comes out, and the pin is not that thick, obviously. All right, so it's a pin. It's a thin pin. It has material around the thin pin, like this. You see here the graded area, and then it has a metallic conductor outside. It's a very popular cable. I mean, this is what we use in a lot of different things. And in TV specifically, because they are high frequencies. And if you did not use this cable and you did not have the outside shielding, this cable would perform like your antenna. Instead of being a cable to send power down to your TV set and home from the antenna, it would radiate the whole thing. And so it would not really work practically. You will see a lot of noise on your screen. So this is a very popular cable. And what we try to do in this problem is just to find the electric field, because the most important thing, as we will introduce today in transmission lines and in passive components like capacitors and so forth that you see, special capacitors, is the capacitance. So for example, what you see, at least for the way I'm teaching this class, is that we will try to get the important, the theoretical foundation for fields, and then apply this theoretical foundation to create equivalent circuit concepts, which like the capacitance, the inductance, the resistance, which then we use into circuit design and into design all kinds of systems. As you know, if I want to design a receiver, I don't use electric fields, but I use local electric fields. I translate their effect into circuit components, and then I incorporate those. Now we are going to continue this after we introduce capacitance today. So I wanted to bring your attention to that. And then the other thing that I wanted to do, going back to home, and I would like to attract your attention to this, go and look at the third problem. At the third problem we solved, it was a problem similar to your homework, but it was not exactly your homework. It says here, it says hints for homework number 4. Now, somebody asked me whether we recorded this session. Usually I record everything. I have included recording to everything we do on Zoom. But I told you that sometimes for some reason, the system is not recording the sessions. And hopefully we see that. In that particular case, neither I or the students noticed that there was no recording. And that's what we discussed at the end of the class. There was no recording, but I think, so there is no recording of the session. But I think if you go through these 3 particular files, you will find everything that you need and go through. In case you have any questions about those, then we have also office hours on Sunday. So you may want to come there and ask me any particular questions. But unfortunately, and I told everybody, as I'm telling you, we need to pay attention that things are recorded. Once in a while, this system does not operate well. Once in one time in 10, the recording does not happen automatically. That's what I've noticed with Zoom. So we have to pay attention. And if anybody sees, like today, we are recording the session, so I can see that. But if for some reason anybody thinks that we don't record the session, you need to let me know so I can initiate that. All right, that's what I wanted to discuss. And now we are gonna go to continuing from what we left on, so these are, so continue here. And where am I? In second, in one of these, okay. I would like to do the following things today. I would like, first of all, to start with this particular example where we will define the capacitance now. And then from there, I would go to the following. I don't know whether last night I brought this out of my files, but I can do this here. But I can see all of my files here. Okay, so this is module 6. Okay, no, I don't have it in module 6. So module 5. Okay, yes, that's what we are going to start today. After we do the capacitance. As a matter of fact, I can start the capacitance from here. This is a file you're going to see, but I will start with this problem and then we'll come to this, do a review, and then we will continue. So today we're going to talk about 2 things, about the capacitance and about the dielectric boundary conditions, all right, which are important. And we will have the chapter we are going, which is chapter 7 in the book. We will have to go through this chapter kind of quickly because we don't have enough time to spend. So we'll do only the fundamentals and then we'll move off to magnetostatics. So we'll do the fundamentals of this chapter today and Monday, and then we'll go to magnetostatics on Wednesday. All right, so now I will solve it here for you. Let's try to do the following. In fact, maybe I don't want to rewrite. So you remember what we said about an infinite plane that is charged? What did we say when we spoke about an infinite plane that is charged? Who remembers how is the field that is excited by an infinite plane that is charged. So here I'm drawing the infinite plane. Okay, so it's an infinite plane. And this plane is charged, let's assume, with all positive charges. And all positive charges are sitting somewhere. Now, this is not a conductor, it's just a plane that has charges. I'm not on a conductor, it's not the charges on a conductor. This is a plane that all has positive charges. Okay, so who is going to tell me? And all are distributed evenly. Okay, so who is going to tell me how the field is going to be excited? What is the direction of the field? And how the field varies as we move away from this?
The direction of the field would be towards the plane.
These are positive charges. How does the field go when you have a positive charge?
Outwards.
It's outwards, all right? So let me write here. You remember this one? How does the field go that is excited from there? It goes like that, all right? Yes? So, okay, perfect. So from here, if this is for a point charge, Q, if you have here a surface charge density, and that's how we saw the surface charge density, then I will use different color for the field. All of the field lines will go like that. Why the field lines are going to go like this and they will not go, they will all go vertical, all right? Upwards and downwards. Does that make sense? That they will be on both sides? Why do I not have anything like this? First of all, it's an infinite, all right? There is no edge. There are no edges on this. This is just a piece of an infinite plane. But why, in other words, I do not have a field that goes, let me use a different color so you see. Why do I not have a field that goes like that? Or like this? Qualitatively, I don't want theory or anything. I don't want equations. Why do you think the field is only perpendicular?
Because it's a uniform field in an infinite plane, therefore the only direction that, like, the only net direction would be perpendicular towards the plane.
Exactly. You know what you said, which was the magic word? Net. That is extremely important in the sentence you just articulated. Net means, of course, every charge of these charges, every charge here is going to have forces, it's going to exert forces like this in every direction, all right? But the horizontal forces, so this is a three-dimensional plane, all right? It's a three-dimensional and a three-dimensional problem. So if we consider Cartesian coordinates, and xy rather, is the plane of the charge plane, is on the xy plane, then practically all the planar forces will be canceled out. Because if you have three charges like this, let me show you, three charges like this, okay? What is happening to the middle charge? There is a force from the left charge that forces it out like this, from the charge on the left. There is another force from the charge on the right that forces it to go that way. And because the charges are uniformly spaced out, of course, I mean, it's like dynamically at equilibrium, as we say, the charges, since the density is uniform, and because we'll assume the density is the same everywhere, so you can think of all of these teeny point charges distributed everywhere, but in equal distances. So these forces will cancel out because they're equal. The same thing is going to apply to this charge next to it because there is another charge that is there. So all of these forces that are exerted on each of these sides, so the net force horizontally is 0. It's exactly what your colleague said. So practically, you are left only with the perpendicular forces. So that is how I would like you to think in electromagnetics. Don't put math first, all right? Math first is death, practically, because math takes you to places sometimes, especially if you're not sure about it. We don't, there is so much we don't know about the mathematical representations yet of the electromagnetic fields that if you start thinking mathematically, you may go into conclusions that are totally irrational. So think physically, think first, think physically, even if, try to think it even, what makes sense to you, because a lot of times what makes sense to you, math is murder. No, math is a language. So let me explain to you why I'm telling you don't use math. Let's assume when I came from Greece in 79, I was speaking English very well for an international student, but I was not fluent. I mean, I could not have a very in-depth discussion with somebody. So it was better for me to use my hands too. Like, because, you use some kind of a mix of a sign language practically. I mean, especially Europeans or Southern Europeans who use their hands very much, is like a combination of a sign language practically and oral. So let's assume now that I was in a group of people and I could understand only half of what they were saying. Not because I'm stupid or anything, I just did not know the whole thing yet. Would I use just my language to communicate some higher level concepts? No, I would murder the language. The language would not murder me. I would murder it. So you need to remember that to use math as a language you are learning is a new language for you. All right, don't over rely on math. Like you would not over rely on French if there was a second language that you learn in high school and now you're trying to learn a little more. You're not going to over rely on something you don't know very much of. So you use it carefully after you have already decided that you know how you're going to approach something, and you use math because then it gives you something more specific. That's so you remember it. Don't be afraid of it. Just know how to use it, and then it will never disappoint you, I would say. so you know. But in any case, so you need to remember that the vertical forces go like this. Okay, what else do you remember? So now that we have decided that all of the forces will be vertical to the plane, what else did we learn in class? And I would like to take you back and see where we talked about it so you remember it. How does this force, or how does this electric field, which is the result of the force, how does it vary with respect to the distance of the observant, of the observator rather, from the plane? If I am, there are two of us, I am here, okay, I'm observer one, and you're here. What each one of us is gonna see? What do you think?
The function is constant with respect to the distance from the plane.
Exactly. Now, that may for you make no sense on the basis of your, say, for example, take voice, all right? The two of us talk to each other. We are close to each other, you hear me. I go a little further away, you don't hear me very well. So the experiences we have from life may not necessarily sustain this finding. And you may have to remember it, but you don't necessarily are quite sure why it's happening. So I will tell you why it's happening. Do you see that? Do you remember the old days that people were using these like horns to talk further away? All right. I mean, now we have amplifiers in the horns where we are speaking, like the crowds, big crowds, and we're talking. There's an amplifier in there. But the old days, there was no amplifier. So we are using this to bring all of the voice into one direction. So why is it that our voice cannot be heard when we go further out? Because the voice, like the electric field from a charge, it goes into all directions. So you are losing the voice because the voice goes into all directions. And what happens as you go away? How does the voice change the intensity with the distance? Like, especially if I could speak on both sides of my head, all right? So I could speak in the whole big, it changes like probably 1/r². Same thing, the electric field. The only reason you are losing the intensity of the voice when the two of us go further away is because the voice diffuses in the whole space. If there was a way for my voice to go into one direction, you could be a mile away and you could hear me equally well as if you were 1 meter away from me. That's what you need to remember. We use that many times. You remember those beam lights that we have in celebrations? The beam lights, why can we see that light on the cloud? And when there is another similar light source, which does not have that kind of beam capability, we don't see them on the cloud. Because in the beam lights, they focus all of the light in one direction, as opposed to allowing the light to diffuse its intensity in 3 dimensions. So it's the same thing here, all right? You move away, remember that. So try to connect electric fields and electromagnetic fields that feel so, what's the right word? That it's so, that you don't understand it very well, connected with things that you have already experienced in real life. And you will see that it starts making sense because you have seen the same things in other things. So if you start relating things, you will never forget it, let me tell you. You will be 80 years old and you will remember that the electric field from a plane, a charged plane, does not change with distance. If you connect it with something that you have experienced. That's the bottom line, all right? That's how we learn. Okay, now we said enough of this. Now that I said that, let me try to take 2 of these planes, 2 charged planes. One is, I will put it up here. One is like this. It's a piece of a large plane, all right? So unfortunately, I have to make it finite, but it is like the one up there that you see. It's like a piece of a infinite plane. So this one, I also show that it has thickness, but in reality it doesn't. It has all positive charges. So it's just a plane. It's not a conductor. Not a conductor at all. It's just a plane. And all has positive charges. And then underneath it, I have another plane, same like the other one, infinite. So it's exactly the same piece of an infinite plane and has the same number, but negative charges. Okay, I'll put a different color for the negative charges. Okay, here, the same number of negative charges. So here, if we assume, let me also do a little bit of this. If we assume that we took a finite size of this infinite plane, so it's like this, all of the positive charges will distribute everywhere. All right. And then we have the same. So this is going to have an area A up here. All right. And then we take exactly the same piece of the infinite charge plane with the negative charges like here. And then we'll have the same area, also A. So the negative charges will be everywhere there, equally distributed. What forces them to be at the same distance? Why are they not accumulated in one place? Like we saw in this shielding, in that metallic structures, that they all go in the corners and stuff. Why is it that the charges are at the same distance among themselves?
Because charges of the same sign tend to repel each other. Exactly. Therefore, like they'll find the most optimal positioning for themselves.
Yes, exactly. Perfect. So now, since we had one plane, we saw the vertical, now we have two planes. So from the up plane, so let's call this plane A, and then let's call this plane B. So the area here, 1 and area 2 are identical. All right, so area A. So plane A, plane B. The field that comes due to the charge of plane A is going to look like this. Okay? And it's going to be EA. How is the field due to charge B? How is it going to go? It's going to go like that. Do you agree? And why? Because the field due to a negative charge goes towards the charge. You remember that? If you have a positive charge, positive, the field goes here, like this. If you have a negative charge, the field goes like that, okay? That's why we have now the two charged field, planes create a field which is along the same direction. Okay, that's very important. What does superposition tell us? What does superposition say?
You can add the fields from each respective component.
Exactly, because then I can do that there is a total field that equal E sub A plus E sub B. There is a total field that is the sum of the two. Do you now remember, that's where you're going to go here, how much, if you have a charged plane like you see up here, do you remember what we found? That the electric field from that is 1/2. The surface charge density divided by epsilon naught, which is the field, all right? I assume that we have air in here. And epsilon naught is the dielectric permittivity of free space. So we have found that E sub A is 1/2 Q sub S divided by epsilon naught, and E sub B equals another 1/2. Now nothing has changed, it's only the sign of the charges, all right? Q sub S, since we have the same charge distribution. Okay, so the total field is Q sub S over epsilon naught. Is that not interesting? What is the other thing which is the result of this? The total electric flux density that is created between these two charged surfaces is how much? This is very, very interesting and very, very simple. So what we remember is that if we have two charged surfaces that have the same surface density, one positive, one negative, we know that what is going to happen? That the electric flux density is equal to the surface charge density. Very interesting. Let me ask you a question. What would happen? How much would be the electric field if both of these surface charges were positive and equal?
Sorry, could you repeat what you said about the electric flux?
The electric flux density that is created between two charged planes, one with positive charge density, one with the equal but negative charge density, is equal to the surface charge density.
Does it have to be infinite?
Yes.
Okay.
For the infinite case. Now, thank you for making this comment, because that allows me, before I go back to ask the same question, to tell you the following. Of course, there are no infinite planes in real life, okay? But what happens is the following. If I now have two finite planes, one, and I will only show the cross section now, one that it looks like this and is charged, finite. And I will make the other one to see how close I'm going to put it. One is like this and charged, finite. So plus Q sub S here, minus Q sub S here. But what is different between this picture, the one picture up there? In this picture down here, the area, or at least this distance, which I call W, is much bigger than the separation between the two planes. If H, and these are finite planes, all right? If H is much smaller than W, which in fact, what does it mean much smaller? That if H is less or equal to W divided by 10, that's much smaller, okay? Then I can safely assume that in this whole area here, the field that I have in between, it's very similar to the field that I have as if the two planes were infinite long. And why is that? So now I'll introduce another term. So thank you so much for asking me this question. This question brought me into something that I always wanted to cover. So now if we have these two planes charged, plus Q sub S, surface charge, minus Q sub S. And if I were, let's assume they're finite, all right? So what would really happen will be that the total field here will be here like this, with this condition, obviously. The total field here will be like that, but at the edges, will start looking like this. Why would it go like that at the edges? Will be a small spillover of the field. Why is that like that?
Because towards the edges of the planes, the electric field is no longer netting zero in the X direction.
Yes, exactly. And also, exactly. And also that if I were to say it in a different way, so I connect with some things we said before, I would say that some of the charges, when I see the edge, they like to go to the edge. You remember what I said, that the charges like to go as far away? Why is that true that they like to go to the edge? Because the positive charges here, I mean inside here rather, I don't want to, I have to be careful on how I draw things here because there is a difference. The positive charges in here, they are feeling those repulsive forces. So as I move towards the edge, these charges, the few charges at the edge will try to go as far as they could, and they will be stopped by the physical edge of the plane. So they crowd at the end, and that's why you see that, which is exactly also, I mean, the way you described it, it's exactly equivalent to what I'm saying. But I think I wanted to connect the two concepts, all right? So, however, because this effect is kind of small, in the context of things, considering that this is such a small part of the field, all right, here, and here, considering everything else in between, what I do in practice, like we are engineers, all right, after all, we say, okay, what I will do, I will take this picture, copy it, put it here, paste, and I will forget about the ends. So I will go here and I will remove this, and even that. And ideally, I would have to also modify the width to find an equivalent width, but I don't do that because I say, well, the change at the end is going to be like less than 1/10 of the whole width, so who cares? So I will assume when H here is so much smaller than W, or W, which is this one, is so much bigger than H, when this applies, then I will assume that my two finite planes are very similar to as if they were infinite. Why is that important? Because now we go into something practical. We cannot realize infinite things in real life. We can realize things like this, where the separation is so much smaller than the width, but we cannot realize things that are infinite. Okay, so now we are going.
Question.
Yes.
So since we have a finite plane, does that mean the charges are not uniformly distributed since we have like more concentrated on the ends?
Yes, so and the ends will not be, no, there are not this many in considering how much charge we have, only a small portion of the charge is going to be unevenly distributed at the edges.
Okay.
And that's why we can ignore it.
Okay.
Otherwise, if it was a big part of the charge, we would not be able to ignore it. But because this is a small part of the charge, we ignore that.
Thank you.
You're welcome.
Professor?
Yes.
Sorry, I have another question.
No problem.
Regarding the 1/10 factor, is that just an arbitrary selection, or does that have that specific?
It's an engineering selection. We normally use it, all engineers, when they do designs, they use that factor. It's a safe thing. You can violate it, go like to a quarter, but then you start getting into like some weird stuff. So you like push your luck, as they say, when you try to go to higher than this. But if it's anything that is if any two lengths compared to each other are less than the relative size, one is less than 1/10 of the other, then we consider that to be much smaller.
Okay, thank you.
Okay, you're welcome. So now, why all of this is important? Now I have placed everything that I need to have to introduce capacitance and a capacitor. What is a parallel plate capacitor, which is the basis of all of the capacitors we have, really? All right, the parallel plate capacitor is nothing else but it's a device, because we are talking about something that we make. It's a device that is made out of two parallel plates. Of course, in this case, they are conducting plates, all right, which look like this, two conductors. They are, they are large in area, but they are in a very tight distance in between them. Now, obviously, since I would like to do some work here, I cannot put them this close, all right, because I would not be able to draw anything in between. So I will draw them like this for now. Okay, like this. And here we will remember that this one, H, if this is W, and let's assume it's a square, it's not necessarily, does not have to be square, all right? It can be like a parallelogram. Even it can be, one of the dimensions can be much lower than the other, but let's assume it's square right now. So the area of this is W squared, the area of the plate. And now what are we doing here? We assume that we charge one of these with a positive charge, Q sub S, and I will explain how we do this charge, Q sub S, and the other with a negative charge minus Q sub S, surface charge density. Okay, so according to everything we said above, and assuming also here that H is much smaller, this is like less or equal to W over 10, all right? We assume it's like a parallel plate, an infinite parallel plate. So now we know that the total field here, see how we take the quick steps? We know how the total field everywhere in between these, E, is equal to Q sub S over epsilon naught. And it's perpendicular, all right? If this is, for example, if this is X, Y, and Z, like this, X, Y, and Z, is along the negative Z direction for this particular case. The minus or positive sign, only it affects the direction of the electric field, nothing else. Okay, what do I do next? Now I define the potential difference between these two. Do you remember that we defined that E equals minus the gradient of V, where we called V the potential function? If we take this and if we integrate, let's assume that I have 2 points. I'll put them with red. So this point P is P1, and this point on the other end is P2. What I do right now is I take the line integral from P1 to P2 of E dot dl, and this is going to give us P1, P2 of the gradient of V dot dl. Since this problem, the electric field has no dependence on X, Y, or Z. It's just a constant everywhere. Therefore, we expect now the V, if there is anything with V, it will only be a Z dependence, but not even that, because the V only depends, for example, well, let me just say that. E has only the Z component, all right? So I will put it like that. N is minus, therefore it's gonna be minus theta Z, V of Z. Do you agree? This is the definition of the gradient. All right, you remember the gradient? How it was? A sub x theta x plus A sub y theta y plus A sub z theta z. So since there is only the Z direction, therefore, from these two, we only use this component, which in fact, therefore, gives us what I wrote up there. All right. Having that in mind, if I plug in there in a question, say between, let me also give it numbers here. If this is 1 and this is 2, then what I find is that P1, P2 is a constant. That dl, so it's along, dl is the Z direction, so it's going to be E dot dz, excuse me, I need to put the direction, the unit vector first, az dz equals minus P1, P2, and gradient of V is nothing else but theta z V of Z, or d V of Z dz, since there are no other variables, dz. And therefore, from here, we have that E, which is a constant and is Q sub S over epsilon naught. And then we have P1, P2, dz equals how much? Minus V, V2, V2 minus V1. And therefore, from here, how much is the line integral between points P1 and P2? How much is the line integral between this point P1 and P2? Is H. Is it not? Yes?
Yes.
All right. So this is,
Oh, sorry.
this is H. So we have Q sub S, H over epsilon naught. And how much is this? Is V1 minus V2. And what do we call the potential difference between the two plates? This is the upper plane. Okay, so this one is, let me see, this is number one. Number one here. One. And the one down there is 2. How much we call the potential difference between 2 points? We call it the voltage. So this is the voltage V between 1 and 2. The potential difference is called the voltage between 2 points. So what is it that we found? We found that these two charged planes here, these two charged planes, that they have a positive charge surface density and the same negative charge, same density, then we'll have a voltage difference V12, which is equal to Q sub S H over epsilon naught. Very important. We call that the voltage of this parallel plate structure. One more thing. Now that we found this, how can I create this situation? Let me take this one here, copy it, and I will go down here and put it back, paste image. I did not want to paste it as an image. Paste. Okay, let's have this. How can we create a situation where the top plate has a positive charge, the lower plate has a negative charge? Same. How do we create the situation in real life? Here it was, we just set it up as a problem, but how do we create that?
We could attach the top plate to the positive side of the battery and the bottom plate to the negative side of the battery.
Yes, yes. Exactly. All right. That's what is happening. So practically, and also the convention, all right? So we use conventions here. Whenever we go from electromagnetic problems to circuit problems, you need to remember that we have to use conventions because the circuit parameters, we make them up. All right, we created the concept of a capacitance. We create the concept of a voltage. These are all made up things so we can work with them. And therefore, the idea here is that if you have a battery, like that voltage VD, let's assume that you take on like a 0.5 volt battery. You connect it there. The convention says that the positive is going to supply positive charges. The negative is going to supply the same number of negative charges. So if you connect, say, a battery to two plates, conducting plates, that's what it's going to do. It's going to create, in fact, it's a small example you can do at home with small voltages. It's not, nothing is going to happen to you. You may just feel a little bit of if you touch it, you're going to feel a little bit of pinch from the charges. But other than that, that's what is happening. So you can create an electric field at home. From two metallic surfaces, take two wires, put a battery. So that's a parallel plate capacitor. All right, it might not be ideal, but that's what it is. So now, if we do that, why do we call even the entity? So let me define it first. So now we have an electric field like that. We have a total charge Q, which is given by Q sub S times the area, which is area here. And I call the area A. So we have a total charge, which is Q sub S A. And it's a positive on the upper, is negative on the lower. So now I can define the following circuit quantity, the capacitance. I define, that's the definition. I define the capacitance as the ratio Q of the charge divided by the voltage. All right. So I define the capacitance as the ratio of the charge divided by the voltage. And what is this entity? First of all, let me apply it here. So if I take Q, which is Q sub S times A, and I divide it by the voltage, and do this here, equal sign here. And the voltage is here, Q sub S H divided by epsilon naught. What do I get? I find something really, really interesting, that C has no dependence anymore on Q. So C, which is I call the capacitance for this structure, and therefore I call this structure the capacitor, a parallel plate capacitor, is equal, only depends only on the geometry and on the material you have. That is extremely important. And why do we call it a capacitance? What does it really show? It shows the capability of this device to store charge. Could you give me an example? Do you know how many capacitors we use in circuits? Exactly. Do you know how how many capacitors we have on like every circuit here on this cell phone? Why? What do capacitors do in circuitry? Which is hugely important. If you go to like a RFIC design, some of you, you're going to use more capacitors than you have thought you're going to use in your whole life. Why is that? Because capacitors is a very useful element. It has the capability to take charge, store it, and then hold it. So for example, if I have a capacitor here, to remind you some things in circuits, if I have a capacitor, and then I have here a switch, and then I have here a source, a voltage, okay? A battery or something. I connect this to the capacitor. Why do I not see? Can you hear me?
Yes.
Yes, we can hear you, but I can't see what you're drawing.
Yes, exactly. So I saw that, but that is probably is a little bit of delay in showing what I'm drawing for some reason. Cancel. I have this problem. You're going to see it. I will just say it. So what happens, because this is where practically done today, but so what happens is that if you have a capacitor, you connect it to a voltage, and then you have a switch. So the voltage, the switch, and then the capacitor. You close the switch, and then all of the charge goes from the battery, as much charge as it can go to the capacitor, as the capacitor can hold, all right, goes there. And then if you open the switch, what happens? All of the charge remains in the capacitor. Now, if the capacitor has a resistance, parasitic resistance, then some of this charge is going to be getting lost over time. However, let's assume that there is no parasitic resistance. Then you hold it there for some time, and then what happens if you have another switch on the other side of the capacitor, and that switch it was open so the capacitor can hold it. If you close that switch, then the capacitor over time can release the charge. So we can time when we move bits, like if I am in a computer and then I have 0 and 1 bits, we can time when we are going to move those bits around. It's extremely important. I cannot tell you how important this simple concept of a capacitor has become in circuits. Is that the most fundamental thing? I mean, if there is anything to know about circuits, like 3 elements: resistors, capacitors, and inductors, and you know exactly what they can do for you. So in any case, now that we have this capacitance, then what we're going to do next, all right? So that's a capacitor. Now, one thing that I wanted to tell you, you remember the units of epsilon naught? What are the units of epsilon naught? Farads per meter, unit length. Do you remember that? So here, what do you have on the capacitance? You have epsilon naught to have farads per meter. A, which is the area, will be meter squares. And then H, which is the length, is going to be meters. So what is the total unit for the capacitance?
Farads.
Yes. So epsilon naught, we call it a dielectric permittivity, but in reality, it shows the capability of the medium between the two plates to hold charge, to hold it without, the capability of the higher the density meaning in epsilon, the higher the value of epsilon. So you see, I was disconnected from the other end. The higher the value of epsilon, the higher the capacitance. Also very important. That's why in some places, we always put in circuits a different material in between the two plates. It's not air, obviously. Of course, we need a material to keep the two plates in a distance, but also it helps us with the capacitance. So now we define the capacitance, and now, next time we are going to introduce on Monday the Neurodielectric Interface. What are the conditions if we have a dielectric in part of the space and air in the other part of the space? How does the electric field relates between the two? And on the basis of that, we'll do a few different examples of capacitors anymore. We're not going to go into, after we define the capacitance practically, we're not going to go back in the capacitor in the electric fields unless we have a reason, but you will see some examples we'll do on Monday. And that will be how far we are going to go here. And then we are going to move into magnetostatics to look at inductors. And then in parallel with that, we'll speak about resistors, which is nothing else but what the resistivity that happens when electrons move, like current through material, through a wire, what happens with the resistance and so forth, and why is that important to know. So that's what we're going to do. I have a quiz for you, which is on the basis of shielding and the things we discussed on Monday and Wednesday. The quiz, I will turn it on right now, and it's going to be available for you to do until Monday morning. Any questions for me?
Yes, ma'am. So what we went over on Monday, Wednesday, and today can be found in chapter 7 of the book.
In chapter 7, let me just get the book for a moment. Yes, the book has a lot more, to tell you the truth. We cannot do all the whole book. It's so much material. In fact, it is on chapter 6 and more. So I will, now that we missed that week, I will go and tell you which sections. So we just did the parallel plate capacitor today, which is on chapter 6.5. We did the coaxial as an example. And then I think we'll do
It's 9 o'clock.
Excuse me, we'll do the dielectrics as part of the last chapter 6. And then we are leaving that chapter on Wednesday. Obviously, there is a lot more there that we have not done. And we'll go to magnetostatics.
Okay.
Okay, so we are doing stuff in the chapter, but we are jumping some areas. There is a lot more material. And possibly what I will do, which I think I need to do for you to help, is to say which sections we have not covered from the book.
Yes, ma'am.
Yeah, that will be helpful for your
Thank
study.
you.
You're welcome. Okay, thank you so much. Have a nice weekend. And we have office hours on Sunday. Take care.